General relativity is physicist Albert Einstein's understanding of how gravity affects the fabric of space-time. The theory, which Einstein published in 1915, expanded the theory of special relativity that he had published 10 years earlier. Special relativity argued that space and time are inextricably connected, but the theory didn't acknowledge the existence of gravity. Einstein spent the decade between the two publications determining that particularly massive objects warp the fabric of spacetime, a distortion that manifests as gravity. Einstein spent the decade between the two publications determining that particularly massive objects warps the fabric of space-time, a distortion that manifests as gravity. The gravitational force talk between two bodies depends on how massive each one is and how far apart the two lie, even as the center of the Earth is pulling you toward it, keeping you firmly low on the ground. Your center of mass is pulling back at the Earth, but the more massive bodies barely feels the tug from you, while with your much smaller mass you find yourself firmly rooted thanks to that same force. Yet Newton's law assumed that gravity is an innate force of an object that can act over a distance.
As he worked out the equations for his general theory of relativity state, he realized that massive objects cause a distortion in space-time. Imagine setting a large object in the center of the trampoline. The object will press down into the fabric, causing it to temple. If you then attempt to roll a marble around the edge of the trampoline, the marble will spiral inward toward the body, pull in much the same way the gravity of planet pulls attracts in space. General relativity has passed all the experimental tests so far, but its applicability is expected to break down when the effects of quantum mechanics, the theory of very small particles, should become dominant. Bends around a massive object such as a black hole, causing it to act as a lens for the things that lie behind it. Astronomers routinely use this method to study stars and galaxies behind massive objects. The two objects align so precisely for images of the quasar appear around the galaxy because the intense gravity of the galaxy bends the light coming from quasar. In case like instance cross, the different images of gravitationally lensed objects appear simultaneously.
Good day everyone. My name is Josh Medina from grade club class A. The orbit of Mercury is shifting very gradually over time due to the curvature of space-time around the massive sun. As the closest planet to the sun, Mercury's perihelion, the point along its orbit that is closest to the sun, is predicted to follow a slightly different direction over time. Under Newton's predictions, gravitational forces in the solar system don't advance Mercury's predestination tends in its orbital orientation. It's measured to be 5,600 arcturians per century. 1 articons in equal to 1 over 3,600 for a degree. However, there is a discrepancy of 43 articles percentually. Something Einstein theory of general relativity accounts for using Einstein theory of cold space-time, the fluctuation of Mercury's perihelion. Tall advance is likely more than under the predictions of Newton. Hence, planets don't orbit the sun in a static elliptical orbit. Sure enough, the several research paper published this the mid-20th century of compared Einstein's calculations of Mercury's perihelion were shown to be accurate. In a few billion years, this bubble could even cause the innermost planet to collide with the sun or a planet. The electromagnetic radiation of an object is stretched out slightly inside a gravitational field. Ten of the dance waves that emanate from Earth Thailand on an emergency vehicle. As the vehicle moves towards an observer, dance waves are complex, but as it moves away, they are stretched out or reflected, known as the double effect. That same phenomena occurs with waves of light at all frequencies. In the 1960s, according to the American Physical Society PTT's Global Thought and Glenn Lipka, South Gamma rays first down, then up the side of a tower at Harvard University. South and Lipka found that the gamma rays is likely dense frequency due to distortion caused by gravity.